Now let's try to focus some time in terms of how we really fit a regression equation from the data, and once we fit it, how do we interpret it, right? So there are so many tools which can do the process compared to the traditional estimation process. Probably interpreting is much more important for us, right? So that's the reason we'll spend more time in terms of one, the fitment of that, and two, interpreting a regression equation, what all the business insight we can derive from that regression equation. So from that perspective, we'll focus on a process called least squares, or in a simpler or in a much better word, it is called as ordinary least squares method. OLS method is what is the mechanism that drives the concept of a regression. We'll try to understand what that means. Now, in any kind of model building process, we are using the data to build the model. The historically observed data we are using to build a model. Of course, there are various models that are being talked about in the business world where we do not use any kind of a data. I can probably talk to the experts and ask them what could be the best possible guess for this relationship, or what they foresee about the relationship between the two variables. Or there could be a brainstorming session in terms of arriving at the possible relationship between the variables. Now, in these kind of cases, I'm actually not relying on my past data at all. I'm actually not relying on the observations that have occurred in the past. I'm trying to use a theoretical kind of guesses and try to consider that as a model. Whereas when we are talking about this entire sessions, our intention is not working with these kind of models. Our intention is purely based on an objective. I'm not using any subjectivity here. I'm not using any kind of expertise or any kind of experience or any kind of biases in the decision. Purely from the data that I am having, data driven facts, I'm trying to create a model. So I'm not going with my gut feel. There is no scope to use any kind of guesswork here. So the prediction that we are trying to do, the model that we are trying to build, is purely from the data that has been gathered in the past. But of course, that doesn't mean that I am discounting the experience of the manager. Obviously, it cannot be discounted. But what we are trying to say is the experience is very, very valuable when I am trying to use it along with the data driven models and methods. One cannot exist in isolation. Probably just an experience or just a gut feel which is not supported by the data is very bad, and just a data support without the experience also will be a disaster. So the best output always comes when I am trying to mix the data driven outcomes, data driven methods and models, when I am trying to combine them with my experience. The overall decision making process becomes very, very valuable. Because once my manager is comfortable in terms of interpreting the data, applying the results, the decisions can be taken quite effectively. So our entire focus here will be more in terms of interpretation of the model rather than the estimation, because majority of the tools like a spreadsheet like Excel or any statistical tool, they have the capability of generating a regression equation with just a click of a button, with just one menu driven item. So there is nothing much in terms of generation, and once it is generated, using that data for estimation is also another one line item, one step item. So even that I don't need to focus more. But the interpretation of the entire bunch of output that is generated by these tools is very, very important. Every result that comes out has a lot of significance as a part of the decision making. So our focus more and more lies in terms of the interpretation of the model rather than the estimation part of it. Now, any data that I look at, okay, let me open the data set. Here, we earlier also we have plotted, let's say, an regression scatter plot. Here we have done a simple scatter plot between the price and the square foot. Okay, and probably it is showing as the size of the apartment is increasing, the price of it also is more or less increasing. And here I am trying to draw a best fitting line. Okay, one is like this. Probably there could be a one which could be like this, or there could be one which could be like this. So probably just trying to identify. I can draw one line which is like this. I can draw one line which is like this. I can draw one line which is like this. Now, out of these all possible lines that I can draw, which one is the best? Right? Which one is the best indicator of the relationship between the price and the area? So how do I really identify? And that identification is done through a process called least squares regression method. And as the word, or probably the correct word for it is ordinary least squares, OLS. This procedure, it tries to find the best possible line, out of all possible lines, by minimizing the sum of the squared residuals. Residual is nothing but the actual minus the predicted. Now, for every line, every possible line, it will with every possible line, it will compute the predicted values, actual minus the predicted, squared, and then the summation of them. So this is what is the square of the sum of the squares of the residuals. Now with whatever the line, this value is the minimum most possible. That is what comes out as the least squares regression method, and that particular equation is called as my regression equation. So the regression line that is coming out is having the shortest average distance to all the points. Now, why only the square? There could be different logics, and at the same time probably there are different other mechanisms. Right, I can minimize the sum of the absolute residuals rather than the squares of the residuals, or there could be any other, but the most popular one that is used in the industry very heavily is that particular model which minimizes the squares of the residuals. Now just to understand the process a bit more, here let's say I am trying to build a relationship between these two. So initially I'll try to build a model called price is equal to some A plus B times the square feet. So let me assume some two values A and B. Let's say A is some 10,000, B is some 50. Some dummy values I have taken. Now when I have taken A is 10,000 and B is 50, I am also looking at probably using this. I am finding out what is called as a predicted value. Now, what is the predicted value? Because my equation is a plus b times the square feet, I'll say a plus b times the square feet. Now, this comes out to be the predicted price, right? By using some dummy values for a and b, I'm getting that this is the predicted price, right? Now, based on this, I'm trying to find out what is the error. Okay, let me find out what is the error. Error is the actual minus the predicted. Okay, this is the error. I am also trying to find out the error squared because we said sum of the squared residual. This is the residual. Error is the residual, or probably I'll call it as residual only, and this I call as residual square. The actual value minus the predicted value is what I am calling as the residual, and I am trying to do the square of the residual. So this is the square of the residual, and I am also talking of sum of the squares of the residuals, which is the summation of all this. Now my intention is, so let's say if this is the line, right? If the line is 10,000 plus 50 SFT, probably this is what is coming out as the sum of the squared residual. Now if I take something else, probably if I take 8,000 plus 75 SFT, again the sum of the squared residuals could be something else. So these are all different lines, right? So we'll see how we come out with the best one. So just to try to understand this slide a bit more, the difference between the observed and the predicted value, the actual and the predicted value, measures how well our model fits the data. So this is the error part of it, or the residual part of it. The residual, if it is smaller and smaller, which means the data is a best fit. The model is a best fit to the data. Now, is this the only error that I can get, or can I get an error which is smaller than this? Now, that should be our exercise as a part of the least squares regression model. It determines the best possible model by finding the line that minimizes the sum of these residuals. So these are typically altered, these two things, in such a way that this becomes the least possible. And why we are doing the squaring? Because the negative or positive residual, both of them are equally dangerous. The big negative should not be offsetted against the big positive. Both of them should be magnified as error. So squaring will always remove the negative and the positive being cancelling out each other, and at the same time the larger the value, the magnification is going to happen, and that is one of the prime reasons the least squares regression method has become one of the most popular methods in terms of building a model from the existing data. Now, okay, now that we are here, I want to do the prediction first. Okay. So for that, one way, what is that I can do? I have to minimize this value by changing these two. Probably a tool like Solver I'll rely on. In Solver, which is an optimization kind of a tool, I want to minimize the sum by changing these two things. Right? And nothing else. I have no other constraints. So this is telling me that this is the way out where I can minimize. This is the minimum possible sum of squares of errors that is coming out. And these are the values of A and B. So which means I am coming out with minus 10,081.07 plus 70.22 times the square feet. So this is a typical expression for the price. So from the data, this is the best possible fitting equation that has come out. Now an interesting thing for us to look at is, I really don't need to do this entire exercise to arrive at this. There are some kind of tools that are directly available. For example, without doing all this stuff, let's say in Excel, I rely on this tool called regression under this data analysis tool pack. I get into this regression. I just need to give the values of y and x. Y is the dependent variable what I want to predict. So I'll say y is the price. This is what I want to predict. X is something which I am using to predict y. So I'll say square feet is the one that I am using to predict y. And the labels are there in the first row. And I'll do the output onto a new worksheet. Right? So, okay. So this is the traditional output that would be given by any statistical package. Now here you see the expression is more or less the similar. Price, the expression is coming out as price is minus 10,091.1 plus 70.22 times square feet. Almost the same. Small things here and there, but almost it is looking like the same itself. So this is the traditional. So without doing this entire activity, we are getting a similar kind of an interpretation here. So the equation which is the best possible is, so this is the true numbers that are coming out for the intercept as well as the coefficient using the least squares regression method only. So this generation process we really don't need to bother, but the interpretation part is very important for us because our decisions are purely based on interpreting this output what is given by this tool. Okay, so the first part which we are interpreting is these two. We know this already. So estimates, so the output whatever we are getting, it is estimating the coefficient of the model. So there is a 70 here. We are getting A, which is this, which is the intercept. So if it means that if the square feet is 0, the price is minus 10,091. Whatever is 1, probably I'll use this regression output 1. Okay, what it is simply saying is, if the square feet is 0, for a 0 square foot house, I am the price of it is minus 10,000. May or may not make any kind of a sense, right? May not be meaningful in some cases, whereas in some cases probably I can derive useful information out of it. But when I look at the slope, it's a very important point, 70.22. What it simply means for me is, for every 1 unit increase in the SFT from 1000 SFT, if I increase my, if my flat is one more SFT, probably I am expecting that the price of that particular flat will increase by $17.22. So that's a very useful insight for us as a part of the interpretation process. All right. Now, okay, are these the only two things for me to interpret? Or even further, what are the other things that are coming out here? Out of that, the most important element that we always look at in assessing and comparing the model is the R squared that comes out. Right? In this case, the R squared is coming out as 30.57%. Right? Here it is coming out as 30.57%. How do I interpret it? It measures the overall quality of the regression model. Right? The quality is 30.57%. That's the way to talk about. the model effectiveness is 30.57%. So it also, what does that clearly mean? What do we mean by the accuracy? What do we mean by the quality? How well the square feet is able to track the price. To what extent the square feet is sufficient enough to predict the price. To what extent the square feet of the building is able to explain the variability in the price. Now that is what is coming out to 30.57%. Now I'll tell you how that number has actually come. Once we visualize this, it becomes more and more easier. Right? Now here I will have to introduce you to three important terms. The total sum of squares, the regression sum of squares, and error sum of squares. So there are different terminologies people use for different. Probably you can talk about three things: the total sum of squares, the regression sum of squares, the error sum of squares. What are these three? All right. When I am talking about the sum of squares, right? Okay, let me, for the time being, let me delete these three elements to start, or probably let me hide them now that we have discussed something on that. Let me hide them. Now, what I'll do is, I'll do a predicted value using the regression model that we have got. What is the regression model? This is the intercept plus the slope times the value. This is the square foot. So I am getting this as the predicted value here. Right? So this is the actual price. This is the predicted price. So from here I am getting my residual, which is the actual price minus the predicted price. And based on this, I am also getting my residual squared, which is the square of this residuals. Fine. So this is the value. Now, okay, what I am more interested in is the three different parts. Right? Let me expand this here. The formatting part, I will take care of it as a I'll take care of this formatting as a number. Okay. So this is the typical number. These are the three typical numbers that are given here. Now I am trying to explain how those numbers have come. For that, first we have taken only these two values. Based on these two values, I have computed the predicted value. And based on that, we have computed the residual and then the residual square. Now, let me try to add all these residual squares that I have got. You see that this number is exactly 636488, 636488. It's matching with the sum of squares here. Then the total sum of squares is nothing but, okay, I'll take the, let me do the average of the price average, right? Price average is coming out to the average of this price column, which is 130 something. I'll take the predicted price average also. Predicted price average comes out with again the same value exact. So that's one important property that comes in a regression. Whatever is the regression model, I see that the average of the original actual value and the average of the predicted value are always the same. Now, when I am talking about this total sum of squares, I am trying to subtract the average from each observation, like a variance, trying to subtract the average from the price. So the contribution to the total sum of squares, what is that I am going to do? Every observation minus the average, I am doing the square of it, right? So this square. So I will try to do the summation of every observation from its average. All I am getting is 916852. So check it out here. It is 916852. This is the total sum of squares. Similarly, I'll do the regression sum of squares here, saying from the predicted value, I subtract the average of the price and I do the square. Okay. So again I can do the summation of the regression sum of squares column, which will give me 200 and, or 280 363. So here you can check 280 363, which means there are three things that are coming out. See, one, when I looked at the average of the actual and the predicted values, they are the same. The other thing that I am trying to look at is the deviation, right? The variation of each observation from its average. I want the variation to be as much lesser as possible. So I am trying to see the variation of each of the observation from its average. And that is what I am considering. And the total variation in my data was around 916. Whereas when I look at the regression model that we have got, the RSS came, the square of the deviation from the mean is coming out to 280 only. Which means when I am taking the residual and the square of the residuals, which works out to error sum of squares, that summation is coming out to this much, which is what is the base for your R squared. The R squared actually comes out as the regression sum of squares divided by the total sum of squares, which is around 0.30, which is the value that has come out here. Right? So this is how this table is going to come out. The sum of squares is going to be the total, whatever is the regression able to take care of. Out of this, probably you can visualize it like this. In my data, in my actual data, this, see, between the actual and the predicted, the average is the same. Now the second thing I am seeing is, okay, average wise, the regression model has captured everything. But the next level, which is the variation wise, to what extent the regression model has captured the behavior of the actual. Now that is what we are trying to see, and that is what we are saying here. The total variation that is present in the original data is to this extent, whereas the total variation that is present in the regressed data is to this extent. While the means are the same, the variations are like this, means the entire variation that is there in the data is not taken care by the regression. Only to this extent the regression model has taken care of variation that is there in your original data. This much part of it is not taken care of by the regression model, and that is where this number divided by this number is what is resulting in the R squared. When I divide by this, this is what is coming out in the form of R squared for us, right? So that is what is the first basic interpretation, which talks about the effectiveness. Only 30.57% of the variation in in the dependent variable, which is the price, is taken care of by the square feet, which means almost the remaining 70% is not taken care by the square feet. What does that mean? The remaining 70% could be attributed to some other variables apart from the square feet, or it could be totally random in nature, which cannot be attributed to any other factor. So that's the way to bring out the interpretation by looking at the outcome of this variable. Right now here, okay, I think we have tried looking at almost all. Let's see. Squaring all the deviations and summing the squared deviations lead to the concept of the total sum of squares, which we have already seen. How much of this total uncertainty or the variation has the regression line managed, which is what is coming out as the regression sum of squares, right? So in the total sum of squares, all we have done is the sample variance. We have measured the overall variability in the data. The higher the variability is, the harder will be our modeling problem. Here the variability is a very high number. So I need to have a regression model which can really address that. Otherwise it's going to be a modeling problem. And it considers the deviations between the regression line and the data point we have already talked about. So these are the actual data points, whereas this is our regression data point. So the difference between these two is what has resulted in a residual and the residual squared. So that is what is coming out with the error sum of squared, whatever is the uncertainty that is left even after applying the regression model. So from there is what we are deriving the R squared of the model, which is an assessment of the quality of the model, right? So it's a clear mention about, if I have to say in one single statement about the R squared, it's a proportion of the total variability that the regression was able to capture. Right? The higher it is, if that comes out to be 95, 99 kind of percentages, it means that regression model is almost a wonder. Right? So if that's the case, where do I say what should be that value of R squared, which I should say this model is good? Is there a way I can say that this model is good, this model is bad? Based on the R squared value, can I say? For that, the simple answer is it depends on the context. See, many a times what happens is the external variables, right? Apart from square feet, there could be various other variables in the data which could influence the price. If I say that the external variables are fully controlled, means they never change. Only the square feet will change, all others will not change at all, which actually is very much possible under the experimental conditions, typically for clinical kind of or medical kind of applications, where generally all the external variables are controlled. Wherever the external variables are controlled, the R squared really need to be very, very high to make a good decision. Whereas, especially in a social science kind of a scenario, where the external factors are very difficult to be controlled, what we simply talk about is even a very small R squared is decent enough to establish a relationship between the two variables. So it depends completely on the context. I cannot come out with a single benchmark number which says this much of R squared is good or this much of R squared is bad. The only thing we can do is we can compare two or more competing regression models against each other. For example, in this itself, let me create a different regression model to start with, where I will introduce one more variable. Right? I'll introduce a second variable. Why only square feet? Now I want to see square feet and bedrooms. Both can influence the price. I want to know not just the square feet. I also want to see square feet as well as the number of bedrooms. Can they impact the price? Now this is where I am actually switching to a model called multiple regression. What is this multiple regression for me? I am primarily looking at two independent variables. Right? Wherever I am looking at more than one independent variable, more than one predictor variable, we are talking about multiple regression. Of course, from the process perspective, there is nothing much for me to do excess. Only the interpretation part we need to be careful of in that scenario also. So here I'll go with a multiple regression kind of a mechanism. Of course, the y doesn't change. It's only the x, wherein I'm considering here two variables. These are the two variables that I'm considering. Rest all is remaining the same. Now you see, first of all, the equation has changed. Now what is the new equation? Minus 6,367.6. Okay, price is equal to minus 6,367 plus 49.49 times the square feet plus 12,486 times the number of bedrooms. Now, this is what is coming out as the new model for me. Now, earlier my model was price is equal to minus 10,091 plus 70 times SFT. Now, what are the key differences in the model? Now, I have brought in even the number of bedrooms into the model. Apart from that, now you could see earlier it was a $70 increase for a 1 SFT increase, but now it is only around $49.50 increase for a one SFT increase in the area. But at the same time, if I am increasing the bedroom, one bedroom, the price of that apartment is increased by around 12,486 bucks. And here, okay, now how do I say which of these two models is a good model? Probably R-squared. Now in our earlier model, the R-squared was 30.5, whereas here the R-squared is 39.29. So R-squared has actually gone up by almost 8 to 9%. So probably it may give me an indication that the model number 2 is much more appropriate, much more better compared to the model number 1. Fair enough. But before I make a conclusion, I need to have some small amount of caution. I need to be slightly careful because of this very interesting property of R squared. It's an unpleasant property that it will never decrease even if we add variables to the model that are complete nonsense. Instead of the number of bedrooms, if I add probably to this data, if I simply add the serial number 1 to 100, it might still be possible that the R squared will not come down. It may go up or it will stay flat. Or even if I add the weights of some random 100 people, right? Or the owner's weight of all these homes, if I just take the weight and height of the owners and I just put it, even then my R squared will not come down. If the square feet is there as one of the variables, and any other variable I am adding, sense or nonsense kind of a variable, it will, the R squared cannot come below 30.57%. So this is where I have to be slightly careful while doing an interpretation, because once I have taken square feet, whatever the R squared that I have got, there is no way I add the second variable, third variable, any nonsense variables I add along with the square feet, there is no way I can get the R squared lesser than 30.57. Now, if that's the case, more and more I'm adding, it results in higher and higher R squared only, though marginal. It can never result in a lesser number, a lesser R squared. So, which means the overemphasis to the R squared should not be done. We have to be careful in terms of evaluating the R squared. Now this is where the other term comes in the spreadsheet, which is called as the adjusted R squared in both of them. In this case, the adjusted R squared is 30.02%, whereas in the second case, the adjusted R squared is 38.32. Generally, in the practical world, we are looking at the adjusted R squared, which is actually a penalization for the inclusion of the nonsense variables. So it completely helps us. This is the one which can really help us in the comparisons part. And to be more precise, this is nothing but, it's just an adjustment from the R squared. Now what is that adjustment? Okay, first step is subtract the R squared. Make it as 1 minus R squared. Okay, do a 1 minus R squared. Then I multiply it with n minus 1 and divide by n minus k minus 1. N minus 1 is the total number of data elements minus 1. Okay, so this number I multiply it with the total number of data elements minus 1, and I divide it by n minus k minus 1, total number of data elements minus the number of independent variables. We have used two independent variables here, minus 1. So this becomes n minus k minus 1. And whatever this number comes out, I subtract 1 from this entire number. Now from this number, if I am subtracting 1, this is what 0.3832. This is what is coming out as the adjusted R square. It's just a manual manipulation, and what we see is this value can be lesser. So if with the two variables I get 30.32%, there is a possibility that with three variables it can come to 30.15%. This is what I mean by penalizing. Now this means I should not include this as a part of my model. This should be my better model. So the comparison between the models can happen quite comfortably when I am relying more on adjusted R squared rather than R squared solely. Now this is what is a typical basic understanding that we need to have regarding the basic regression. Of course, there are a few more elements that are there here, which we'll try to take them up in our next session. But up to here, it's expected that a comfort level is required with respect to understanding the coefficients, the R squared, the adjusted R squared, how we look at the total sum of squares and error sum of squares and the residual regression sum of squares. All this thing should be comfortable, and once you have the equation in place, this is your equation, so you can use this equation to simply predict what should be the price. If this is the SFT for a house, if these are the number of bedrooms that are there in the house, what should be the price of this particular house? Some such kind of a quick calculation can be done to do the pricing part. But of course, a few more things are there which we'll discuss them out in our next session, right?